Alright, next up is a physical pendulum, problem 48. It's dealing with a stick, essentially. Pivoting at the end here, and eventually, for part B anyway, we'll be dealing with it as it's pivoted 10 degrees. But first off, for part A, we need to figure out the length of the rod, L. And in doing so, what else do they give us? They give us the mass of the rod, 0.5 kilograms. They give us the period. It's going to be useful. And the angle. So we know that the period of a physical pendulum is 2 pi times the square root of the moment of inertia of this physical pendulum divided by mgh, where, as I screwed up in the main concept video, this is not like a height, which, by the way, just to confusify things, we're going to need to find. It's not this height that the center of mass drops. It is the distance from the pivot point to the center of mass for this particular equation. Right? Strangely enough, in part B, we're going to need mgh, which is gravitational potential. That's different than this. So we should use a different letter. In fact, I'm going to break out. I'm going to do it. I'm going to quickly replace it with L over 2. Not a new letter, just... You were excited, right? You were like, he's going to make up a new letter for this. What is he going to use? What is it? No, sorry, I'm not that brave. I'm just going to replace it with... Oops. L over 2. Now I feel better. Alright. So the other thing to remember is, what is the moment of inertia, the I, of a thin rod pivoting at the end? So maybe you remember that from back in the good old days of chapter earlier. 1/3 ml squared. That comes, by the way, from the moment of inertia of a rod pivoted at the center, which is 1/12 ml squared, plus the parallel axis theorem, where we do m times this distance squared. Anyway, that's where the 1/3 comes from, and that's all over m g L over 2. M's cancel, one of the L's cancel, and we can rearrange this slightly. This 2 goes up to the top, and the 3 we can go to the bottom, so 2L over 3G. And what are we looking for? Oh yeah, we know T, and we know G. We're solving for L. So algebra, alakazam, alakazoo. We get L equals 0.838 meters. That wasn't too bad. Now, part B is asking, what's the maximum kinetic energy? Which, by the way, happens at the lowest point, right? Maximum potential, no kinetic because it's stopped. Speeds up, lose potential, gain kinetic, maximum kinetic, lowest point. So here gravitational potential is turning into kinetic. And so UG equals KE. UG max equals KE max. And that's MGH equals KE max. So we know M is 0.5. We know G is 9.8. We just gotta find H, which H is this little, this little, this little distance, the distance that the center of mass drops. So from here to here. So let's we got, this is L over 2. This is also L over 2. Draw a line here. Center of mass is here and here in both cases. I basically didn't draw the bottom half of the rod. This is 10 degrees. This piece right here is H. This is L over 2 minus H. So we could do cosine of 10 equals adjacent, which is, we'll call this x. X goes from here to here, equals x over hypotenuse, L over 2. So x equals L over 2 cosine 10. And we know that h equals L over 2 minus x, right? H is, L over 2 is the whole distance from here to here, so h is L over 2 minus x. So that's L over 2 minus L over 2 cosine 10, which is L over 2 times 1 minus cosine 10. Anyway, long story short, what does h equal? We use the L we found in part A there. H equals 0.00636 meters. Stick that in here, and we get mgh, which is Ke max. So I'm just going to put that equals 0.0312 joules. So that was pretty cool. Conservation of energy, physical pendulum period, moment of inertia, geometry, lots of good stuff. Alright, how many more? That was 48. 2 more problems to go. So I'm doing a lot of problems in this chapter because it's just, well, there's quite a few sections, but I just think there's a lot of unfamiliarities about these problems that I wanted to address, and so it turned out that I needed to do a buttload of problems for that to happen. So anyway, 2 more to go. 49's next.